with some simple but interesting ideas, okay? Today, I'm going to talk about statistical interaction for quasi-particles. Therefore, I need to define what is quasi-particles and what is statistical interaction. Let's go there. Some materials, lattice, that are formed by lattice, they may present low energy excitations that behaves more or less like a Dirac particle in its bidimensional faithful representation, but with a Lorentz breaking term. And this Lorentz breaking term is associated to the quasi-particle drift velocity, which has information about the macroscopic content of the lattice, okay? And we can talk about TMZ materials, graphene, eddy states, and depending on the case, we can talk about massless and massive Lorentz broken modified Dirac equation. We can talk about how the model it has analogous lattice structure with intrinsic magnetic flux. Therefore, discrete symmetries are broken, and we have a quasi-particle with a mass gap, but different mass gaps in each valley, okay? This valley, I need to explain my terminology. When I say valley, I'm talking about independent low energy excitations or quasi-particles arising from low energy of excitation of this lattice. We can manipulate this degree of freedom in technology, for example, in the field of electronics. And it can be useful to store information even in quantum computing or things like that. Let's talk about our prototype of lattice, the graphene, or more specifically, the honeycomb, the so-called honeycomb lattice. Look here, please. The A and B sites are not equivalent. Why? They have different crystallographic definitions because the neighborhood of the A site is different from the neighborhood of the B site. Let's evaluate what's the basis for this crystal. Is the delta 1, 2, and 3. Let's see their definitions. It's interesting to see that Marino has an interesting book about this kind of quantum field theory applied in materials, okay? The crystal base is defined above. We have the order of magnitude of this site in nanometers, and we can use the model due to Wallace node model associated to the interaction between creation and annihilation operators associated to the A and B sites, summing over the positions and summing over the spins. It's a well-known model. The T parameter has 3 electron volt order, is of this order. You can find interesting information in Gorbig material. The Hamiltonian can be conveniently written in momentum space, and we have equation 2. We can define a spinor with these two creation and annihilation operators for the A and B sides. The energy is given by expression 3. Now is the point. We analyze low energy excitations and define what we mean by quasi-particles. We can find 2 points of low energy, K plus and K minus. What it means? We call it valley excitations, 2 independent valley excitations, we can do a canonical transformation in this Hamiltonian and obtain equation 6 for both of these excitations. It remembers the Dirac Hamiltonian in its two-dimensional representation. It's in 2 plus 1 dimensions, we have a two-dimensional representation for Dirac equation. And this is indeed the faithful representation in this dimension, of course. All of these equations are very well known, but it's good to remember. The drift velocity is associated to T and A parameters, then define the microscopic content of the lattice, and has these emergent properties in low energy. Of course, let's go ahead. If you plot the energy profile around the Brillouin zone, we can find K line and K points of minima, the so-called Dirac cones. Why cones? We can look, it's simple to see. And for this, we can, how can I say, define Dirac-like dispersion in these low energy points. Of course, we are trying to give a continuum representation, discussion, for a lattice discrete matter. Then it must be accurate. According to equation 7, we have an accurate description associated to this cutoff, which is related, of course, to the size of the lattice. Let's go ahead. For graphene, we obtain a kind of massless quasi-particle. But a mass gap can arise if there is a kind of asymmetry between A and B non-equivalent sides of the honeycomb lattice. It can occur due to spin-orbit interaction or due to the presence of different atoms in A and B lattice. For the case of graphene, they are the same atoms. Of course, this energy gap associated to a kind of mass term for this lattice is of order for silicon and germanium given above. It's interesting to see something about discrete symmetries. Look above. Both, in this case, for this kind of material, both valleys have opposite masses, and it guarantees it avoid any kind of discrete symmetry violation. But we can also talk about Haldane model. Haldane model is a theoretical model with intrinsic magnetic flux between the plaquettes. But the interesting point is that Haldane model violates discrete symmetry due to the presence of intrinsic magnetic flux scenario. And then we don't have a relation between the valley masses. Okay, now I will talk about the specific content of my talk. I will use natural units, then this valley velocity is smaller than 1, since light velocity is our upper bound. If we are in a scenario of discrete symmetry breaking, we can talk about some specific kinds of self-interaction between these valleys. We define the current in the first ethane. I forgot to put an equation, no problem. And we can derive this three kinds of statistical interaction. This statistical interaction is non-local and violates discrete symmetries. But in a Wilsonian perspective, they can arise in this kind of scenario. I will show how to introduce the magnetic field in the later slides, okay? Then I put three possible kinds of interaction. We can use Gaussian integration and introduce some bosonic field to write this interaction in a, how can I say, in a local form, the model. It resembles the model used by Zhang when he talked about fractional quantum Hall effect. It's not our case, but there is an analogous structure between the theories. Then I can write a local interaction theory for the first kind of statistical interaction in terms of an auxiliary B field. We have the definitions. Here we have a structure associated to Lorentz breaking and the associated propagator for the quasi-particles. This is for type 1, not other type. What we are going to do here is to consider vacuum corrections for both the bosonic and the fermionic part, okay? It's qualitatively analogous to lump shift discussion. We're going to find vacuum corrections associated to the nonlinear self-interaction of the valleys. This kind of induced self-interaction can be used in technology, in electronics. It's important. Therefore, we are going to show that they have interesting topological structure. First of all, Chern-Simons action is not gauge invariant. However, the functional generator from which we take all the physics of the model can be invariant if we fix the K coefficient to be of that form. Let's come back there. It enters as a normalization of the propagator of the auxiliary Chern-Simons field. Therefore, we will need also to think about non-perturbative Heisenberg approach, Nakanishi B field. We can do a bridge between theoretical investigation with an interesting motivation due to this physical scenario. But for big enough Ni, we can try to find some perturbation scheme. I did both things, the non-perturbative and perturbative. I will put just the perturbative. The perturbative result for the bosonic part is a well-known one, very simple and well-known. The polarization tensor, it arises in first order just due to a loop, a single loop, and we have this structure. Something interesting can be obtained if we look at the antisymmetric part of this polarization tensor. It's associated to a shift of a generalized transverse conductivity. This limit is an exact result, although we are using one loop approximation. It was proved by Dudal and collaborators as a kind of generalization of Coleman theorem. And this is important because for condensed matter, we have a scenario of broken Lorentz. Then, of course, we can say, oh, Coleman theorem, okay, but is it valid also for this condensed matter scenario? Yes, it's a recent paper. Then, we can safely say that for this type 1 kind of statistical interaction, we can, if we put some test charges and test currents, we can arrive at this transverse conductivity, not to be confused with Hall effect. We didn't put any field yet. And we are allowing a more general scenario with different gaps for valley 1 and 2. We can use, if we have isotropically broken Lorentz series, what we can do, we can use the same approach than thermal field theory. You can look, it's well known, projectors, and we can find the polarization tensor in this scenario. The first one was for relativistic, okay? But the conclusion is the same. I will talk about that. That's the simple part. In the simple part, okay, we have this expression. But if you want to talk about physics, we need to find it explicitly. And I will look at the static limit to find the potentials. Then it's important to find the explicit expressions, okay? The conclusion regarding the transverse conductivity is the same for relativistic and non-relativistic. It's interesting. Well-known result, but interesting. They are kept, and even for non-isotropic case, with a more violent breaking of the symmetry, even breaking the isotropic one, we have the same conclusion we can show regarding transverse conductivity. It's very simple to find that. Now, if we have the normalized structure, we can put test charges and evaluate what happens. We can find the analogous of the scalar potential, have this form in terms of Bessel function. But there's an interesting thing. If we take the bare action with this test chart, we can say, oh, nice. We have attached generalized magnetic flux and then anionic statistics. But if we consider the more realistic approach with all the radiative corrections, we see that the point like here is BC is the generalized magnetic field. We need a kind of generalized magnetic field to talk about some Aharonov-Bohm effect. But there is a cancellation of the delta-like behavior, and we have a path-dependent Aharonov-Bohm effect. That's an interesting thing. Maybe some models that are built in order to furnish attached magnetic fields and chain of statistics must take it into account. Okay? Here's the definition of our parameters that appear here. We have the velocity, the drift velocity that's associated to the microscopic content of the model, the lattice, the intensity of T parameters. We have the mass gaps associated to the physics, have a physics origin, as I mentioned. And we have the definition of the renormalized constant. Oh, if we have discrete symmetry on the matter sample, equation 2 ends do not have this sign. They cancel out. Okay, that's an interesting part. There's a book from an author called Shen, and he have talking about topological insulators. They use as the model a kind of, how can I say, modified Dirac equation with some new terms, like some p-square terms that don't appear in Dirac equation. It guarantees some topological content for the model. I did the calculation for the relativistic case, but I'm trying to provide the non-relativistic one. But there's an interesting thing. The topological content of this kind of model is defined by this Charney number. The Charney number is a functional of the fermionic propagator, its spatial momentum variations in zero energy frame. It means that the Lorentzian structure and the most commonly used Euclidean one share the same qualitative topological properties. for our specific case, this Charn number is given by equation 23. But okay, why I'm talking about these radiative corrections and topological properties of the valleys? Because if you can manipulate its properties, we can talk about maybe some, how can I say, applications in technology or something like that. We need to know how these kind of things interact, okay? And there's an interesting thing. If we talk about topological insulators, which is not our case, because the topological insulators have discrete symmetry, and if we talk about even Hall effect, we have extended states near the boundary, concentrated on the boundary. And there is a relation between this topological number and the existence of these boundary states. Then they are associated to this non-trivial topology of the system. We can take this general expression and try a tentative solution like 25. We are defining our mass, energy-dependent mass in 26, and what I was speaking is in 27. Non-vanishing Charn numbers, Charn number implying lambda 1, lambda 2 bigger than 0. And if we have that, we have a non-trivial solution concentrated in the boundary, which is a phenomenological signature of this kind of model. Okay, type 1 interaction, if we consider discrete symmetry on the matter sample, gives one valley become topological with this kind of boundary solutions, and the other is trivial. If we use type 2 interaction, we need two auxiliary bosonic fields with opposite normalization. Then both valleys become topological with opposite drift velocity. In type 3 interaction, there is no fermion mass correction, at least in that one loop. And therefore, the valleys are trivial, topologically trivial. And this type 3 interaction can be described by means of a BF theory with this kind of coupling. Okay, I will not talk about temperature, but there's just a final observation. If you have a gas of 3 photons, normal photons, Maxwell photons, we have the functional generator with a given normalization, and we can talk about some temperature effects. But what about Charny-Simons? Charny-Simons don't have asymptotic particles. Then, if we just have free Charny-Simons, we need the Grassmannian ghost, the first, and associated to gauge symmetry is a very well-known thing, and we will have an operator determinant normalization for our partition function and a non-trivial partition function, but with no asymptotic photons, Charny-Simons photons. What can we do? The second term is a bosonic ghost. It's well known in literature, bosonic ghost, and this kind of pseudo-differential structure appears naturally in other contexts of electromagnetic fields projected on a plane. Therefore, it's well known, this kind of pseudo-differential structure, and it has well-defined properties, although I admit that it's strange. With this extra bosonic ghost, apart from the Grassmann one, we have a trivial partition function for the free case. Of course, when it's interacting, there are some radiative corrections for the partition function, but no, if we just consider free Charny-Simons one, of course not. Then, in order to put the magnetic field, we would like to take the whole vacuum correction structure, perform the parallels substitution, and we can use creation and annihilation operators to find a version of this Hamiltonian and generalized expression for Landau levels. It's important to recover the correct units. We are used to work with natural units, but we lose a lot of physics. It's a very good exercise to recover the units to achieve the Lorentzian breaking part, and that's all.
Thank you for the very nice talk.
Thank you very much.
I have two questions. One regarding the nature of the Chern-Simons terms that you are considering. Is it abelian or not abelian because of the quantization?
It's abelian. It's abelian.
And yet you achieved the quantization of this Chern number.
Yeah. I noticed that if you do the radiative corrections for the valleys, something that no one did until now, we arrive at a kind of structure. It's from the same, it has the same topological class from some other well-known ones used in topological insulators case. Then we can use these and find also interesting content for our specific case, and we can take Landau levels, doing parallel substitution, and then we can talk about a lot of theoretical and also some phenomenological things.
Okay, thank you. The second question has to do with the p-square correction to the Dirac equation. Have you tried some sort of transformation of Foldy-Whitehouse type to diagonalize the effective equation? Because you have mass.
This one?
Yeah.
Or the previous?
That self-energy comes from a p-square correction or modification to the Dirac equation, right?
No. G's we normalize the fermionic response. If we introduce that valley nonlinear interactions between the currents, the associated renormalized fermionic response have this p-squared term. It's a simple exercise. But what is interesting is that I found out that it's useful in another context, topological insulators. And it has some non-trivial topological nature. And then we can do parallel substitution in this specific structure with this Lorentzian signature and try to find which are the response in terms of the levels.
Okay, thank you very much.
Thank you.
Thank you for the talk. A very short question. I mean, your models still stay at the level of the tight binding model, nearest neighbors on the graphene lattice. You didn't consider next to nearest neighbors because this introduced a modification in the dispersion relation, introducing k-squared terms.
Yes.
And those terms, okay, they are smaller, of course, but they are relevant if you want to compute the quantum Hall effect levels.
Yeah, there's a very interesting thesis from Federal University of Rio de Janeiro. Then he considered this second order expansion for the Haldane model. My idea is the following. In that case, it's known, it breaks Lorentz symmetry, but my idea is, okay, they must have the same form, analogous form, not the same, but they arise due to different situations. It's interesting to see that depending on the magnitude of this mass gap, one or another can become important first. Okay, then it's if one or the other is more relevant, is associated to the physical scales of a given specific sample. Of course, we can find some hierarchy between this mass gap and the lattice parameters that define the second order corrections, as you said, that are very important. Depending on the hierarchy between them, you have just this one, or just the other, or both.
Okay. Okay, we're on time. Please thank the speakers again.
She wants to make a question.
Thank you for the talk. I mean,
thank
what
you.
defines if you have a non-vanishing chain number is some relation between the charge K and
No.
M?
The non-vanishing charge number it's associated, I've forgotten the name of the reference, okay? But it's associated to a functional of the fermionic.
No, I know, but I mean, from your expression, you have, I mean,
Oh,
to
this
have
is-
the first term
the non-
different, I mean, it will be plus or
second one.
minus 1.
The
So it cancels if it's minus 1 and plus 1.
Okay. G's, how can I say?
So for not to cancel,
Yeah.
you need some specific relation
Okay.
between charge K
okay.
and MR.
Okay,
So
okay,
could you
okay.
comment on that?
Okay, it's important to associate. Here is just, oh shit. It is just the fermionic response associated to the self-energy. If we put all the structure, considering also the free part, but plus this radiative one, this p square part, if it has a relation, a sign relation between the coefficient of this p squared part and the generalized part for the mass, if we have a given relation, a sign relation between them, we have non-trivial topology. But we can have this kind of structure, but depending on the signs between the parameters, you have complete trivial ones. It's associated to the sign. That's why the type 1 kind of interaction have one value topological and the other trivial. That's associated because both will have this p squared, but one's topological and the other not, due to this sign between.
But how is it reflected here? I mean, because each term is associated to one different value, right?
Yeah.
So one of them should vanish for if you say that one is topological and the other one is not.
No. If we do all the calculations, careful calculations, we note that this kind of interaction that I am considering, if you consider the renormalized fermionic structure for the two values, here I'm using just a general n. You can put a label if you want. Then one value has a positive mass, but the other is negative. But we have a modulus in the p square. That's why we have different sign relations for each value. Then we can have fun and change the behavior of the things. That can be used in some technical application.
Yeah.
That's the point. Thank you.
Okay, we're on time, please. Yeah,